Ready? Good morning, everyone. Can you guys hear me okay? Yeah. All right. So my name is Gavin Gear, and I'm a program manager at Microsoft. I've actually worked at Microsoft for 11 years and have worked on a few cool projects, including Microsoft hardware with keyboards and mice. I worked on the tablet PC platform where we worked with the inking fundamentals. And now I'm working on the sensor and location platform. Recently, my oldest daughter asked me a question at the dinner table. And that question was, Dad, what's your favorite thing about work? And I had to think for a minute, but the answer was clear. It's really when I'm able to see something work for the very first time. And over the course of the last year, I've had the opportunity to see new things in Windows 8 work for the very first time. And with location and sensor technology specifically, there's really something exciting about seeing the magic of an app or a system-level feature that just responds to the user or responds to the environment. And it's really fun to use your creativity and imagination to use this technology in ways that really leave people saying, how did you do that? That kind of thing. So today, I'm hoping that with what you've learned here at the Build Conference, with the hardware that you've received, and with what we talk about here today, that you'll be inspired to write applications for Windows 8 that use location and sensor technology, and you can share it and impress your colleagues and families and friends. So let's talk about what we're going to talk about today. We're going to start by really taking inventory of some of the experiences that we can bring to life with location and sensors, specifically in Metro-style applications. We'll then take a focus on location awareness, and we'll talk about what you can do with location awareness, and we'll talk about how you can implement support for location awareness in your application. Then we'll move on to sensors. We'll start with some basic and intermediate scenarios, and then we'll move on to this exciting new technology in Windows 8, which is sensor fusion, where we bring multiple sensors together, and we can use that technology to do powerful and amazing new things for Metro-style apps. When you leave today, you'll have examples of how to effectively use location and sensors in your applications, and you also learn how to innovate with the latest sensor technology. Windows 8 empowers you to build apps that can seamlessly adapt to your customer's environment using sensors and location. How is this possible? Well, to start, the Windows runtime for Windows 8 provides simple and powerful interfaces that you can use in your Metro-style application to implement support for this technology. Sensor fusion really takes it to the next level for sensor technology. It's almost like going from standard def to high def. We can now implement powerful interactions with motion and orientation sensor technology in our apps. And these can be simple apps, or they can be direct 3D apps that really leverage the full potential of all that sensor fusion has to offer. So today you'll learn what sensor fusion is, you'll learn a little bit about how it works, and you'll learn about how you can implement support for sensor fusion in your Metro-style app. One of the really important things about Windows 8 for sensor and location technology is the ability for an application developer to know what capabilities they have. And so today we're going to talk about mobile PC form factors for Windows 8, and we'll talk about what sensor technology is included for those form factors. Another thing that is important is that PCs have sensor technology and location technology that's available and consistent from one hardware form factor to the next. So we're going to talk about Windows certification for sensors and how we're making major investments to make that a reality. So when we were designing Windows 8 and when we were planning with our ecosystem partners what we should include, we really focused on the types of form factors that can really use this technology to its full potential, and also those PC hardware form factors where this sensor and location technology is really critical to having a system that functions well and to having applications that can provide meaningful experiences for these mobile devices. So I'm happy to say that if you're writing an app and you're targeting tablet and convertible tablet form factors, any of these form factors where you're in a slate mode or can convert into a slate mode, Windows 8 systems will have a comprehensive set of sensors as standard equipment. So first we have the ambient light sensor. And the system uses the ambient light sensor to automatically adjust screen brightness depending on what lighting condition the user is in. And that's great because in dim environments, we can ease eye strain on the user when their eyes are adjusted for dark lighting conditions. And we can also save power by dimming the screen in those lighting environments. When the user steps outdoors into harsh ambient lighting conditions, the screen brightness already automatically adjusts up so that the user has an easier time seeing what's on the screen. But your apps can also take advantage of light sensor technology to create cool ambient experiences and to increase the usability of these apps in a wider variety of environments. Windows 8 tablets and convertible tablets also support the latest motion sensor technology. So on all of these PC form factors, you'll find a 3D accelerometer, you'll find a 3D gyro, and you'll find a 3D magnetometer. Those are the hardware components. What you'll also find is the sensor fusion that ties all of these hardware components together to expose powerful capabilities for applications. So this is great news because if you're targeting these form factors, you don't have to wonder if this hardware and these capabilities are present. You can just know that you'll be able to use them. So it doesn't stop with sensors. We also have comprehensive support for location. So one of the investments that we made for Windows 8 was to include the Windows Location Provider. And this is a location provider. It's a virtual device that uses Wi-Fi access points and your IP address to pinpoint the user's location whenever they have network connectivity. So that's great when your users are indoors. What about outdoors? Well, for all systems that support mobile broadband hardware, GPS is available as well. So regardless of whether your users are indoors or outdoors, they're likely to have location data available, and your apps can take advantage of that location data. So let's transition to talking about the apps. Let's talk about location awareness. I like to think of adding location awareness to your application as increasing the relevance of the experiences and the content that you provide support for the user. And I want to start by showing you just a quick demo of a Metro-style application that a team of interns put together this summer that uses location awareness. So here we are in Metro, and this is actually an application that's installed on your Samsung Windows Developer Preview device. We can hit Near Me and find nearby things, right? So we've all been working really hard. It might be time for a big night out, right? So depending on the different type of experience we're interested in, whoops. Let's go back. Sorry about that. Let's plan our big night out. So because this app is location aware, we've been presented with a set of nearby points of interest filtered on the category we're interested in, which is a night out. And we can very easily just select one of these items, very clean UI, very simple user interface, tap on a simple button in the app bar, and we can get directions, right? So when I'm traveling like I am right now, I really appreciate having this type of functionality available because I'm just interested in what's within walking distance, really. So that's a simple example of a Metro-style application that uses our location. And it's actually quite easy to add this functionality into your application. So the world is a big place. There's a lot of places people can go. There's a lot of information out there on the internet. But by adding location awareness to your app can make the world a smaller place for your users. And I want to walk you guys through a couple different categories of features for location that are divided into two different types of location access models. The first model I want to talk about is single-shot location access. And this is the type of interaction that you'll model in your application if your app only needs to update its location infrequently or in direct response to some user action. So we saw with Near Me an example of a Metro-style application that looks up our location when we launch the app and then provides us tailored results when we go to execute a query by tapping on the UI. It's a simple example of a single-shot location access app. We could also write a Metro-style app that uses the built-in webcam to acquire photos, and we could geotag those photos when they're saved. So later, when our users are organizing their photos or sharing them with friends, they can refer back to that location to show these photos on a map or have another way to categorize their content. We could implement support for a basic mapping application. So this could be as simple as showing the user a map, and when the map loads, we center that map view based on their current location. We could support local info apps. This could be location-aware weather, news, sports. There's really a wide variety of experiences and information delivery mechanisms that we can tailor based on the user's location. We could also implement something like social networking check-in. So if we have a social networking app, we want the user to take specific action to check in somewhere, right? Because essentially sharing their current location is private information. So they need to initiate that action, and when they click on that check-in button, we can do a single-shot location lookup, use their location to provide them with a list of nearby businesses and places where they could check in. So these are really just a few examples, really just the tip of the iceberg, ideas for single-shot location access. On the flip side, we have event-based location scenarios. And these are the kind of scenarios where you're going to need finer-grained control over the user's location. You might need more accurate information, and you also need to respond to the user's movement. So the first scenario that comes to my mind is a navigation application where we're going to need to be continuously recentering the map view based on the user's movement, and we might need to snap them to streets, provide turn-by-turn directions, things of that nature. So this is an example of kind of the most demanding type of application for location. We could also do real-time location-aware notifications. So if a user is at home or at work, we could present them with a list of tasks that are really only relevant to the place that they're currently at. It could be a great convenience. So we talked about points of interest. If the user is running our virtual tour guide app, we could actually give them notifications based on nearby points of interest as they're driving through a city or walking by on foot. So it's another way to provide sort of points of interest, but in more of an event-based type interaction model. If the user is using our app while they're shopping in our store, we could provide them with promotional deals and discounts and coupons, things of that nature. So giving the user relevant information is really the goal, and using event-based location access is one of the ways that we can implement that type of functionality. So we talked about the user manually checking in to a social networking app. Once they've checked in, we can provide them with an auto-checkout experience. So say they've moved more than a particular distance from where they checked in, say it's 1,000 meters, for example. We could monitor their location updates with event-based location access, and then once they've exceeded that threshold, automatically check them out. So this is just a few examples for the single shot and event-based location access. I'll definitely kind of lead this up to your imagination and based on the apps that you're currently working with regard to how location fits into that model. So let's talk about what it takes to add location support to your app. The first thing that we need to do is declare the device capability for location. So I talked about the ability for us to write a webcam application that could acquire photos and geotag the photos. If we were going to write such an app, in our app's app manifest file, which is the file, it's an XML file that contains metadata describing the app and declares its capabilities, we would see a couple specific entries, one for the webcam, one for location. And we need these to declare these capabilities because the webcam exposes sensitive information, and so does location. So in order to interact with Windows and the store, we need to have these capabilities declared up front. And I'm showing you XML here. Visual Studio 11 actually provides you with a UI to configure your project where you can just check boxes for the capabilities that your app uses. Once we've declared the device capability for location, once we actually run the code that accesses location, the user sees a consent UI. And this is really, really important. It's important that we instill our customers with confidence with respect to how their sensitive information is being accessed. So the good news is we don't have to write any code in our application to get this to work. Windows 8 does this on our behalf. All we need to do is declare the device capability, which is a prerequisite to actually accessing location, and then write the code that accesses the location. The rest is really up to the user. So let's take a look at some code. We talked about single shot and event-based location access. First here, I want to show you the single shot location access. The first thing we need to do, which is highlighted here, the first line, is create a geolocator object. And the location functionality is contained within the windows.devices.geolocation namespace. Here, we can use the constructor for geolocator to get the geolocator object, which we'll use to access location functionality. So once we've instantiated the geolocator object, if we want to perform a single shot lookup, we can call the getGeoPositionAsync method. And what this does is it returns an object that uses the then pattern in JavaScript. So the first parameter to the then method is the success handler, and that's what I'm showing here. You could also supply a failure handler in case location data wasn't available or the user hasn't given our app access to location. So once the location data is obtained, our getPositionHandler event listener method gets called, and we can access the location data. Here we're showing grabbing off the latitude, the longitude, and the accuracy. So as you can see, it's very simple and straightforward to use the Windows Runtime API for location. And this is single shot. Let's take a look at the event-based location access. And if you didn't look closely here, you might not even see a difference. The pattern looks very similar. We create our geolocator, but then instead of calling getGeoPositionAsync, we're going to call addEventListener and hook up an event listener for position changed. And this position changed event listener gets called whenever the user moves and whenever movement is detected by the underlying providers of location. So here, what I'm showing is responding in the onPositionChanged event listener to the user's position changing. And it's pretty much the same pattern here. We have an event args parameter that gets passed, and we can access the position and the corresponding data members that are exposed there. So, two different ways to access location for two different interaction models. I do want to note that you're not restricted to just using the Windows Runtime API. Windows 8 also supports the W3C API. This API is a standards-based API that is supported by many of the popular browsers today. Some differences I want to point out. First, the W3C API supports a maximum age property that you can set, and that's used to filter out location data that might be older than your app is interested in, the irrelevant data. The Windows Runtime API provides a movement threshold property. And what you can do is set this movement threshold property, and that threshold gets applied to filter when your position changed event listener gets called. So we talked about the auto checkout feature for our social networking app. We could set the movement threshold to the distance the user needs to move before we auto check them out, add an event listener, and then in the event listener, we just check them out. It's a convenience because you don't have to calculate the distance yourself. So those are a couple minor differences. The real major difference is that the W3C API only supports JavaScript, where the Windows Runtime API supports JavaScript, C#, and C++. So you can use .NET, C++, or JavaScript. So depending on your requirements and depending on the code that you're working with and your experience, you can really use either one. So let's change gears and talk about sensors. Before I get into the details, I want to show you a quick demo. And you guys are going to be the very first people in the world to see a new device. This is a device that I concocted in my garage, and it's called the Sensor Head Cam. So, you can see all you out there. It's looking a little magenta. I don't know what's going on there. We're on laptop 2. Yeah, okay, so I've got my Samsung Windows Developer Preview device. Oh, that looks much better on my display. And this is another one of the apps that's installed on your device that you can use. And this is probably a type of application that you've seen before. And this is, it's got a little bit of glare there. There we go. So this is an application that a team of interns put together this summer here at Microsoft. And it allows us to just tilt the device in order to control the motion of the ball. There we go. That's a little bit better. So this is a Metro-style application written in JavaScript. And it gives you a really quick example of using sensors in a Metro-style app. Looks like we're going to have to work on seeing that a little bit better. So this is the type of application that you're probably familiar with. We've all seen a Labyrinth-style application. We've probably all used it. And it makes sense that we need to use sensors for this type of an application. But as it turns out, most apps can benefit from sensors. Sometimes it's obvious because it's a primary driver for the user experience. Other times it's more subtle. So I want to start by talking through some of the basic app scenarios for sensors. And these are simple interaction models that your app can implement support for. The first one is shake. So the accelerometer object in the Windows Runtime supports this method called onShaken. Not a method, it's actually an event. And your application can very easily tie an action, which is the user shaking the device, to a specific reaction, which is whatever your app wants to do in reaction to that shake gesture. So it could be as simple as, shuffling media or refreshing some experience or web page or drawing application for that matter. Users kind of get the fact that they can shake their device, and if the app supports it, the app can automatically do something for them. The next scenario that we think is a real important fundamental is rotation. And so Windows 8 has auto rotation for the screen built in, end to end. In Windows 7, we learned that there were some issues with graphics and with display modes, and it was a real challenge to implement good screen rotation. We've mitigated those issues in Windows 8 and worked very closely across the Windows division to deliver a rotation experience that's snappy, and it has a very pleasant, quick crossfade if you transition from portrait to landscape, that kind of a thing. And your app can sort of ride along and just get auto-rotated. But in some cases, that's not desirable. In some cases, your app is going to want to provide a more tailored rotation experience. So if we had video playback in our app, for example, we wouldn't want to have the animation between portrait and landscape interrupt our smooth video playback. So what we can do is set an orientation preference. Any app can say, I want to run in landscape mode or portrait mode or landscape flipped or portrait flipped. And that will suppress screen auto-rotation when our app is running full screen. That allows the app complete flexibility over the user experience. So in our video playback app, if we did want to support rotation, we could just supply the orientation preference when our app starts up, and then we could use a sensor called Simple Device Orientation. This is a simplified representation of the device's orientation in 3-space. We could then just rotate our video element or implement whatever experience we want to implement support for. We could also do partial content rotation. So if we have a nice background image that's 16 by 9 and we don't want that moved around or scaled, we could just have that 16 by 9 image move with the device, and then we could then take text, for instance, and always orient it so that it's right side up and readable, that kind of thing. So just a couple ideas for you to think about with simple device orientation and rotation. There's another thing that we can do with simple device orientation, and that's supporting the flip interaction. So the simple device orientation sensor also includes the face up and face down orientations of the device. So this is another way that we can take a specific action, the user taking the device and moving it from face up to face down, and tie that to a specific reaction, which would be something like muting the microphone if we're implementing a VoIP app, or toggling the play-pause mode, depending on whether the device is face up or face down in a media playback app. Again, lots of different things that you could do, and I'll let you think about how that relates to what you're building. So I want to move on to what I call intermediate sensor scenarios. And this is taking the next step to deal with raw sensor data and to perform some basic interactions in our application using that raw sensor data. So the light sensor is one of the sensors that we can use for this type of feature. So let's say we have a navigation application. What we can do is tailor the view in our app or the way that we render our view in our app based on the current lighting condition. So when the user is in a dark environment, we can provide a more pleasing view to the eyes when they're adjusted fully to dark lighting conditions, or provide sort of a cool ambient effect that is more of a delighter. When the user moves from darkness to normal indoor lighting, they really have the ability to see more detail, and eye strain is really kind of at a minimum, I guess you could say. It's a favorable lighting condition. So this is where we could have a more full fidelity view. We could have more detail. In our app here, we've got streets and satellite imagery overlaid. We really have the ability to have that sort of full view for our app. But where it really gets useful to the user, I feel, is when they walk outdoors, because this is where users have most difficulty when it comes to reading content on the screen. So what we can do here is, if we have a dial for the readability of how we're rendering our view, we can just turn up that readability dial. We can increase the size of elements and text. We can use bolder lines. We can use bold text. We can selectively use colors that are higher in contrast. This, in conjunction with adaptive brightness for the screen, can really help users to have a better user experience in a wider variety of lighting conditions. Another intermediate sensor scenario would be casual games. So we saw an example with the Labyrinth app of using the 3D accelerometer to control the motion of the ball. And that is an intermediate scenario because really we're taking real gravity, which the accelerometer measures, and we're kind of modeling that as fake gravity in our application so we can move around this pretend ball. So it's really kind of a linear input-output type of a thing where we've got some scaling factors in between to control kind of the response of the ball, that kind of thing. We could also model rotational and twisting gestures and interactions using the gyro. The gyro gives us the rotational speeds around the X, Y, and Z axes of the chassis. So that's another thing that you can use in your application to provide new and novel experiences. So I want to walk you guys through the Windows.Devices.Sensors namespace so that you can understand all that's available for your app to use, specifically with respect to sensors. We start with simple data, where we've got the simple device orientation sensor that gives us our portrait and landscape orientations, plus our face-up and face-down orientations. We've got some raw sensor data sensors, the light sensor, the accelerometer, the gyro. And then we've got these powerful new capabilities with sensor fusion data sensors. So we've got a tilt-compensated compass. We've got a 3D inclinometer. And we've got device orientation, which 3D applications can use to model novel new types of high-fidelity interactions with motion and orientation. So this is what you have available to you. Let's take a look at some code. So the code I'm going to show you here is for accelerometer, but it's really representative of all the sensors except the simple device orientation sensor. That sensor is a little bit different. So sensors are exposed in the Windows.Devices.Sensors namespace. And when we want to use a sensor, we take the name of the sensor, that object, and we call the getDefault method. And this is a pattern where we're returned an object that represents the built-in sensor that we're interested in here. So here our accelerometer variable contains an object that models the built-in 3D accelerometer on the hardware that we're running on. The next thing I'm doing here is adding an event listener for reading changed. So this class of sensors, really all the sensors other than the simple device orientation sensor, expose readings. And readings have two things. They have a timestamp that corresponds to when the sensor data was sampled, and then they have the individual data elements that are exposed by that particular type of sensor. So in our on-ACK reading changed event listener here, this event listener gets called whenever we have new accelerometer data available. And we can access, off of the reading that's in the event args, the individual data elements, which here are the acceleration X, acceleration Y, and acceleration Z members. So in that labyrinth style application in the event listener, they would take the X and the Y values and directly influence the X and Y velocity of the ball, for example. So this is a simplified example, but it gives you an idea of how you would use sensors from JavaScript. So I want to show you a video that will really let the interns do some talking about their experiences this summer building the Labyrinth application.
Hi, my name is Matthew Bailey, and I'm a PM intern here at Microsoft. So after considering a lot of different ideas, my team finally decided to develop a Labyrinth-style game for Windows 8.
Hello, my name is Digvijay Singh Shaktawat. I spent the summer as a test intern at Microsoft. To start, I started exploring different options available to control the motion of the ball, looking into different sensors available on the device. For example, device orientation, inclinometer, gyro sensor. I ended up using raw accelerometer data to control motion of the ball.
Hello, my name is Noam Samuel. I spent the summer as a dev intern at Microsoft. We wanted to use this exciting new platform in Windows 8, so I was tasked with writing our casual game in JavaScript using the new Windows APIs. took just a few lines of code to transform our keyboard-controlled game into an accelerometer-controlled one. Once we had sensors hooked up, we simply tuned a few parameters to make our game feel right.
For my next Windows 8 application, I would love to incorporate the light sensor and have the application change moods or feelings based on the lighting conditions around you.
For my next Windows 8 application, I want to take the users to virtual reality. I want to pick up this tablet, see it as a window, and go into a different world.
So there you have it. There's a brief overview of what our interns did this summer. And actually, we've got a couple of them right here. So if you want programming tips, inside story, you might want to bug them afterwards. So what's really impressive about what they were able to pull off is the fact that, as you could see with the clipboard in the video, they didn't have hardware. They didn't have, in some of the builds, a working debugger. They didn't have things like IntelliSense. And yet they were able to deliver a complete end-to-end experience for a casual game, even with all of those challenges. So really, I think you guys are kind of spoiled. You guys have a device with all these sensors built in. You have a great build. You have a great Visual Studio 11 Express build. And I really hope that you guys will take those devices and really play around with these capabilities. And if nothing else, run the game that they built and see if you can conquer the seaweed level. So I want to move on now to talk about sensor fusion. And this is really an area of technology that has just emerged really for consumer electronics over the last couple of years. So I want to show you a couple quick demos. And hopefully we have a little bit better video quality here this time with the head cam. Laptop 1. Okay, we'll go back to laptop 2 here. Okay. So we're going to be looking a little red still. But what I wanted to show you guys is first a very simple example of sensor fusion. So you guys might have recalled from the, looks like we got a bit of glare there. Okay. Adjust our angle. Sorry, there we go. That's a little bit better. Okay, so you might have recalled from the keynote that Mike Angiulo showed this car steering wheel sample. And what this shows is the use of the inclinometer in a metro-style application. So you can see we're having a little bit of an issue with the angle there. It's the very first proof of concept. But what I want to show you is the behavior. So this uses the yaw axis of the inclinometer. And specifically, we're tying rotations around the axis that points out of the screen at us directly to rotating the steering wheel. So it's extremely responsive, as you can see here. So if I rotate the wheel, it just responds in a very high fidelity type of way. We can also actually rotate the steering wheel when we're down on a flat and level plane, and that's because the sensor fusion is transitioning between using the magnetometer and using the accelerometer, depending on how we're holding the device. And it's also jitter-free. So if I hold the device stationary, if I can hold it stationary, you can see that the steering wheel is very, very still. And I didn't implement any filtering logic in this app. It's just basically using inclinometer updates and applying them directly to the rotation of this transparent PNG image, which is the steering wheel. One additional thing that I want to show you here is that we support the light sensor. And I think for this one, I'm actually going to go back to the console here. So I talked about supporting sort of ambient experiences and providing that little bit of delighter with the light sensor. Well, here, if we tap on the light switch, we can go into an auto mode for our application for the headlights. So if I remove the light source and cover up the ambient light sensor, we can automatically toggle on and off the dash lights. So that's just that extra little bit of functionality that you can add to your application to delight users. Another sample that I want to show you is a sample that our DirectX team put together. And this one is an existing Direct 3D SDK sample that they've added support for sensors to. And this specifically uses the device orientation sensor and uses quaternion data from this device orientation sensor. We'll talk a little bit more about quaternion data in just a moment. So I want to get back to my 3D first-person mode here. So I'm going to go back to the laptop mode. So what I can do is I can take this device and I can, oops, there we go. There we go. Okay. So I can take the device and I can basically use it to look around in 3D space. And I can pretty much have like a virtual reality type of experience. And it has touch support, so I can fire at these targets by just looking around in 3D space. So this is kind of a first effort and the first time that we've really seen this type of sensor fusion in a 3D game. And if you want to know more about this, my colleague Jason Strayer is going to be presenting on that on Friday for direct 3D input experiences for games. So just a quick example, a little bit of a taste. And I'm sorry for the quality here. If you want to see this and play with this in person, you can come to the hardware booth and find our team, and you can play around with this. But it gives you two examples. One really simple and straightforward example using a JavaScript-based Metro-style application and some very simple code. That was 3 lines of code to turn the wheel. The other example with the simple 3D game is more of taking it to the next level with Direct 3D. So with sensor fusion, the whole really is greater than the sum of the parts. Using individual sensors is important and can provide some really great foundational experiences and extra functionality in applications. But when we put these different sensor inputs together, we get something that's truly more powerful than the sum of the individual elements. So sensor fusion really is taking multiple sensor inputs and either enhancing outputs or synthesizing new outputs. Let's take a look at a typical 9-axis system. This is the type of system that's standard equipment on all tablets and convertible tablets that are designed and certified for Windows 8. So we start with the individual sensors themselves. We've got the 3D accelerometer that measures linear acceleration and acceleration due to gravity. We've got the 3D gyro that measures our rotational speeds around the X, Y, and Z axes of the device. And then we've got the magnetometer that measures magnetic field strengths along these 3 axes. In some cases, the data is merely passed through. So the accelerometer and gyro sensors are essentially the raw data coming right off the sensor. The real magic happens when we use sensor fusion to tie these inputs together. So the blue boxes on the right-hand column all represent sensor objects that you can use directly in the Windows runtime. We've got the compass is the first sensor fusion sensor I want to talk about. This is a tilt-compensated compass that your app can use to always know where north is, regardless of how the device is being held. The inclinometer gives you the yaw, pitch, and roll angles, if you think of an airplane, rotations around the X, Y, and Z axes that represents the device's orientation in 3 space. We saw an example of using yaw in the Metro steering wheel app. With the inclinometer, however, there are some issues that you can encounter, especially if you use multiple rotations. there are some ambiguities where multiple rotations interplay. And there's also a phenomenon known as gimbal lock. And these issues really mean that if you need full 3D experience in your game, you want to use the last sensor fusion sensor I'm going to talk about here, which is the device orientation sensor, which exposes quaternion data and rotation matrix data that's free of these issues and problems around gimbal lock and rotation ambiguities. So let's talk through some app scenarios. I showed you the Metro steering wheel app. It's just a simple sort of visualization of the type of input experience that you could model for a car racing game. But you could also use this type of sensor data in a casual app. So there's really a wide variety of things that you can do with the inclinometer. With device orientation, we saw this sort of first-person shooter type experience. And that's using the quaternion data. That's really just the tip of the iceberg. I don't know about you guys, but I've been creamed by my friends playing Halo on the Xbox. With the controller, it's just, I am all thumbs, literally, no pun intended. But when I picked up a Windows 8 tablet and I just moved it around in 3-space and just tapped on the screen to fire, to me that felt a lot more intuitive. So there's games, there's augmented reality, virtual reality. You could imagine pedestrian navigation with points of interest nearby and directions. This is going to be one of the areas, I think, on Windows 8 where we'll see a lot of innovation in apps. And the fact that you have Visual Studio and DirectX and this cutting-edge sensor support all available at your fingertips means that you can really take it to the next level with your apps. So I want to talk real quick about this quaternion data that I demoed in the 3D sample. I talked about the fact that the inclinometer has some issues with multiple rotations. Well, with the quaternion data, the reason that it's able to overcome some of these issues is that really under the covers there's a single rotation around a vector that's continuously calculated. And there's a bunch of fancy math involved in determining quaternion data and in processing quaternion data. But don't worry, you don't need to go running for your linear algebra book because there are some simple and straightforward ways for Metro-style apps and with DirectX that you can leverage this powerful data without tearing out your hair trying to figure out the math. So we start with the Windows runtime. The Windows runtime gives us our quaternion data via the device orientation sensor. We can then feed this quaternion data directly into DirectX Math APIs, right? So there's an X, Y, Z, W value. These are parameters that DirectX Math supports natively. So essentially, we can take the data from here, put it over there. We can use SDK samples and reference documentation to understand the types of transformations that we want to work with DirectX Math. And then we can apply it to our environment. So in the 3D sample that I showed you, we were essentially just moving around the camera in our 3D environment based on the orientation of the device. It's a very simple way to model a user looking in different directions. But we could also manipulate other objects in our environment using this data. And again, Jason Strayer on Friday will be covering this in more detail with the direct 3D input for games. So I want to step back to our more simple example with the Metro steering wheel and go into a little bit more detail. Mike in the keynote flashed up the 3 lines of code. I wanted to talk to that a little bit more here. So in this particular sample, we are using the inclinometer. We call the default method to get the inclinometer object. We start off also by getting a current reading. Since the yaw rotation is really with respect to the magnetic North Pole, when the device is down flat and stationary, we really want to center the steering wheel around that initial yaw angle and then just rotate it based on relative motion, right? So we grab the reading, and we have that as sort of our default inclinometer position. We then add the event listener. So every time the inclinometer data changes, our event listener gets called here. And then we're just able to calculate the offset angle for the yaw axis, since the yaw axis is the same axis as the steering wheel, would be modeled in a real car. The second line of code down in the event handler is just getting the element for the transparent PNG image from our document. And then we apply a transform to rotate the image based on the relative yaw inclination. So this is just a simple example of using inclinometer from JavaScript in a Metro-style application. So, lots of information. I just want to recap real quick here. Windows 8 empowers you to build applications that can seamlessly adapt to your customer's environment using sensors and location. And this is possible because Windows 8 provides the simple APIs in the Windows runtime that your app can leverage to model basic scenarios, intermediate scenarios, and also tap into the full power of sensor fusion. Windows 8 provides a consistent hardware platform for sensors and location. We talked about how for tablets and convertible tablets, Microsoft is making strategic hardware investments with our partners to make sure that this cutting-edge technology is available for apps to use on all of the applicable hardware form factors. And finally, Windows certification means that when you write an app on your PC, you can be confident that when your customers are running your app on their PCs, they get a consistent and reliable user experience. So I do want to point out real quick the related sessions. Building great Windows 8 systems is kind of a high-level overview. Architecting and integrating sensor drivers, 249, will be going on in the Orange County Ballroom in the next hour, where I'll talk about this technology from a hardware standpoint. And then finally, on Friday, we've got 754, which is where you can dig into more detail and hear more about the end-to-end input experience in Direct 3D for games. We've also got a bunch of helpful documentation. We've got white papers and documentation online where you can learn more about these concepts that I introduced today and learn more about how you can use your Samsung Windows Developer Preview device to write these types of applications and to really tap into the power of location and sensors. You can also reach out to us directly by emailing our external inquiry aliases, which are also included here, one for location and one for sensors. If you're having issues or want to find out more information, feel free to reach out to our teams, and we can point you to the correct forums or get you the information that you need. So, I really want to thank you all for coming and spending time with me today. In order for us to continue to deliver the best content possible, I would just really like to ask you to fill out the session feedback forms, which are here online for you, so that we can know what you're interested in hearing and what resonated with you. So thank you. I'd like to open it up now for questions. Looks like we have a few moments for questions if you guys want to line up to the microphones.
Quick question. There we go. So can you speak at all to what they're doing with Visual Studio to support emulation of different sensors? In particular, geolocation would be helpful. Obviously, a device is going to be more useful for other types of sensors.
Yeah, right now, I can't really disclose anything about the specifics for simulation, but feel free to contact me via the external inquiry aliases, and I can follow up with you later on that. Over here?
Yes, on the phone, there are certain things that you have to do to take the device and let go of the device, exclusivity, dealing with power on and off. Do you have to worry about with those things on Windows 8?
So I'll go into more detail with regard to power states and interactions with apps in 249. One thing that's important to note is that your app has access to sensors, a Metro-style app, when it's actually running in the foreground. So one of the important power and performance concepts was to suspend apps that are in the background. And when apps are suspended, they don't have access to sensors. There is an exception for location if there is support for background tasks, and I can point you to the appropriate people if you're interested in learning more about that. Sensors are also powered down when the system is in connected standby. So when the screen is off, we power down the sensors to maximize battery life.
We don't have to worry about writing code to unsubscribe from events and resubscribe
Nope.
or anything like that.
We've built that support in. Yep.
So you mentioned something about a magnetometer at the beginning, but I didn't see anything that you mentioned in the framework.
Yes. Yes, the magnetometer is sort of the neglected child of sensors because it doesn't have this sort of top-level sensor object that exposes it directly. But it's the sort of key contributor both to the compass. The accelerometer, gyro, and magnetometer actually implement support for the compass, but it's also used for the inclinometer and for the device orientation.
So there's no plan of actually exposing that through something we can
Correct.
access from? Okay.
Correct. If you want to know more about the sensor fusion specifics, I will be going into a little bit more detail about how sensor fusion works in 249. Yep.
So 2 pieces. I mean, look around the room. Everybody's got laptops. I didn't see
Yep.
any sort of scenarios where you're seeing sensors being implemented in laptops. And 2, what about other types of sensor types like pressure sensors that could determine elevation where you're at on a floor, so you can do building mapping, or temperature sensors, kind of control temperatures of the laptops, or environmental influences.
Okay, so the question is, what about laptops and other sensors? So our main focus was really making sure that tablets and convertible tablets work great, right? They're kind of the bigger brother to the phone, and sensors are really critical there. For laptops, sensors are still relevant for sure. Light sensor for adaptive brightness of the screen, that kind of thing. So the Win32 APIs for sensors, which I didn't really talk to here, support a wide variety of different types of sensors. But we didn't invest as heavily in those scenarios because we really wanted to nail the fundamentals for mobile scenarios. So sensors are supported on laptops and other form factors. In fact, if you have an all-in-one PC with a rotating screen, the accelerometer can be used to do auto rotation there, right? That kind of a thing. But most of our investments are really around nailing Metro-style apps on these more mobile form factors.
What about proximity?
So we do not have proximity directly in the Windows runtime, but we do support it. We have a HID sensor class driver that is new for Windows 8, and we've pushed the standards for that as well with partners in industry, and that supports human proximity sensors. Up front?
In your slides, you said that the GPS is only available with mobile broadband.
Yep.
Is that a hard restriction?
Nope.
Or is that just
Yeah,
the default implementation, and if you include standalone GPS, you can provide a driver interface?
absolutely. Yeah, it's just when you have mobile broadband hardware, you have to provide the GPS functionality there, right? So a lot of
Okay.
these systems will have it. You could also have a dedicated standalone GPS radio, things of that nature. Yep.
From what we've seen, it looks like there's a lot of sensors for internal hardware. What about communicating with external sensors and devices such as ANT plus devices and stuff like that? Is there any?
That again is going to be a Win32 scenario. So the platform definitely supports that. PCs can be integrated, attached nearby, that kind of a thing, and they can describe themselves as such. But again, we really wanted to focus on the device itself, right, for tablet and convertible tablets. So the Windows runtime APIs are all really focused on that level of support and don't support the other sensors that would be connected or wireless, that kind of a thing. But the platform, again, if you had a more vertical type of scenario that you wanted to implement support for, we have all the pieces there for you to be able to implement that type of scenario as well.
Okay, thank you.
Mm-hmm. Question over there?
Yeah, on Windows Phone 7, out of band in CodePlex, there's a shake gesture library to kind of roll up, give you a higher level of abstraction over accelerometers. Any plans? Is some element of that in here that I missed?
Yeah, so
How do mere mortals work with all of this data?
Yeah, so you can use the shake event from the accelerometer directly, and you don't have to write any code to do that. You can also consume raw data from the accelerometer and perform whatever type of motion, activity, gesture detection that you want to as well.
But you're not creating that higher level abstraction API.
We have the shake event that accelerometers can support,
Okay.
but it's actually not a hard requirement in Windows 8.
Great, thanks.
Yep. And the API, the Windows runtime does support that on shake and event right off the accelerometer.
The GPS provided in the Samsung tablet, is that hooked to the mobile broadband, or will that work if you are not?
The driver that you have for the device does not fully bring up the GPS functionality on the Samsung Windows Developer Preview device. That's something that we're working with our hardware partners on, but the functionality didn't quite make it in time for build for GPS.
Software ability or hardware ability?
It's really, I won't go into all the specifics, but it's not fully functional.
Can we expect that as part of the updates?
I can't comment with regard to the updates, unfortunately. So I just encourage you to keep checking and check the hardware forums, that kind of thing, and we'd certainly announce that if that were to happen. One more question?
Can you comment on NFC support? Is there?
So NFC is actually a parallel technology. It's not implemented directly through our APIs for sensors proper. I do know that we have sessions here on NFC, and they're all these sessions are all recorded. So if you missed one, I'd encourage you to catch it online. Thanks again, everyone.